Hi, we're Matmerize, the new standard for polymer design. Today we'll be looking at a use case using our platform, PolymRize. PolymRize is our flagship product. It's used for polymer and formulation design, combining years of research in materials informatics into a cutting-edge online platform. It features an easy user experience, custom machine learning model training, and property prediction capabilities. One of the main material design workflows that can be implemented on PolymRize is called active learning. Active learning is particularly useful when you want to design a new material starting from a small dataset. Active learning can be used for two purposes. The first is to discover new materials with outstanding properties efficiently, and the second is to improve model performance intelligently. So, how does active learning work? You start with an initial dataset and train a custom machine learning model on PolymRize. Then, you create a list of candidate materials and run predictions using the machine learning model you built. You can then use the results from these predictions to guide which experiments you perform in the lab. If your goal is to improve the performance of the model, here you run experiments on the candidates with the highest prediction uncertainty. If your goal is to discover new materials with specific properties, you run experiments on the candidates which were predicted to have the properties of interest. From these experiments, you generate new experimental data points. You can then augment your initial dataset with these new data points and train a new model using this augmented dataset. You repeat these steps until you converge on a material with the desired properties. The example we'll look at today will focus on how to use active learning to improve the performance of a model. We'll be using a dataset on organic photovoltaic materials found in literature. This dataset contains several fingerprint variables, including molecular and processing parameters. The dataset also contains the target property, which is the power conversion efficiency, or PCE. This is the property that we'll be interested in predicting. The dataset contains a total of 115 data points. For this example, 86 randomly selected data points will be used for model training. 20 data points will be held out for the first active learning cycle to represent new experimental data being generated. Finally, 9 data points will be held out for validation. The first step of an active learning cycle is to start with an initial dataset. Let's take a look here at our initial dataset. The columns here correspond to processing and molecular variables. The second step of an active learning cycle is to train a custom machine learning model on the initial data. Let's go to PolymRize and see how it's done. First, we click the Train Model tab. Next, we select the CSV file that contains the data we want to train on. Then, I select the column name of the property I want to predict. That column name is PCE. Next, we have options for which prediction type we want, which fingerprints you want to include, whether or not you want to augment your data with our data, and if you want to generate a learning curve. For now, let's leave these options at their default settings. Next, we can set the name of the model. Let's name this model PCE Model 1, and then we select a category for the model. For simplicity, this model falls into the category of other properties. Next, we can specify a unit, which is percent, and a number of decimal places for the predictions. Let's leave that at 2. Now, just click Start Model Training. Once a model is trained, a helpful diagnostics report will appear to help you understand the model. Notably, you're able to see helpful error metrics like the R-squared value, root mean squared error, and mean average percent error. Also, we show you a parity plot to help you understand how well the model did. Finally, we show you how the feature space of your training data is distributed using principal component plots. So now, model training, the second step of the active learning cycle, is complete. At this point, we have an initial model trained on a small dataset. We can use this model to prioritize which experiments we should conduct in the lab going forward. Let us simulate this by considering 20 data points taken from the complete PCE dataset. Each row here has not been seen by the models previously, so each row represents one unknown material that we're interested in. Let's use our model to predict the PCE of each of these 20 cases. We'll navigate to the Predict Screen tab. At the top of the screen, we can see the model we trained earlier. Let's select it. Now let's upload our dataset for prediction for our 20 unknown materials. Once the data is uploaded, we simply click Predict Properties. The predictions for these 20 cases show up in an interactive table. In this table, we can sort property values and we can reorder columns. We can use this uncertainty information to our advantage. Namely, our model will be improved by getting the true values of the points for which the initial model is most uncertain. To choose which materials to experiment on, we use the sort feature on the uncertainty column and select the top n rows with the highest uncertainty. In this example, let's set n to be 10. This takes us to our next step in the active learning cycle. This step requires generating experimental data for our 10 high uncertainty points. Once we've generated this experimental data, the first step of the active learning cycle is complete. We start the second active learning cycle by adding the 10 new data points to our initial 86 data points and training a model on this larger data set. Let's do this on PolymRize. We'll train a model as we did before, but this time selecting the new data set of 96 points. Let's name this model PCE Model 2 and train it. As before, we see a diagnostics report for this new model. Now we have two models, one from each active learning cycle. For comparison's sake, let's train a third model. This third model will be trained on the initial dataset plus 10 of the 20 unknown data points that had the least uncertainty. Let's name this model PCE Model 3 and train it. So, now we have three models all trained on different datasets. Let's compare the three models by seeing how well each can predict the PCE of unseen OPVs from the complete dataset. These 9 OPV data points have been held out and not used to train models 1, 2, or 3. We can compare how the models do on these points by going back to the Predict Screen page. Let's select the three models we want to get predictions from. Now, we can upload the dataset for prediction. Let's see how each model performed, starting with Model 2. As a reminder, Model 2 was trained on the initial 86 data points, plus 10 more points that PolymRize suggested using active learning. So, it should perform the best. We find that this model is able to predict power conversion efficiency to an error of just 0.53%. Let's move on to Model 3. This model was trained on the initial 86 data points, plus 10 more points that PolymRize did not recommend. This model should not perform as well as Model 2 because it disregards active learning. And indeed, we find that this is true. The error here is 0.78%. Finally, let's consider Model 1. This model should perform the worst of all models because it has seen less data than Model 2 and Model 3. Again, this intuition is confirmed. The RMSE here is 1.17%. In conclusion, we can see that active learning is a powerful tool for increasing the prediction accuracy of models, and these algorithms go far beyond what is possible with simple linear regression. Of course, the ultimate purpose of having an accurate model is designing new materials. And by using active learning, you can build reliable models which will allow you to accurately expand your search and intelligently plan your next experiments. Thanks for listening. Please feel free to reach out for more information.